Okay, let's jump right in. We're seeing this huge global push for carbon neutral energy, right?
Absolutely. It's everywhere.
And a massive piece of that, everyone's talking about it, is green hydrogen. Using renewable energy to split water.
Right. Good old electrolysis.
Ah,
H2O into H2 and O2.
simple concept, but tricky in practice sometimes.
Well, yeah, you've got two reactions happening at once. There's the HER, hydrogen evolution reaction,
Yeah.
making the hydrogen gas. That one's usually pretty okay. But then you've got the OER, the oxygen evolution reaction, making the oxygen. And that one, that's often the slow step, the bottleneck.
Ah, the OER. So that's what holds back the whole hydrogen production process, makes it less efficient.
Exactly. It needs a good kickstart.
Yeah.
Which means you need really efficient catalysts, especially for alkaline OER, which is common industrially.
Catalysts, right. And traditionally, what are we talking about? Nickel-based stuff.
Yeah, conventional nickel catalysts are, well, they're common. They're relatively cheap. They do the job, sort of.
But there's a catch.
There's always a catch. Yeah. The big limitation is often the active surface area, getting enough of the nickel actually touching the electrolyte where the reaction happens.
Okay, so you need more contact, more interface between the catalyst and the liquid.
You got it. Maximize that contact. And this brings us to the really interesting stuff we found in the sources for today's deep dive. A discovery about a material that, frankly, behaves in a totally unexpected way.
Unexpected how? Not just a slightly better catalyst.
Not just slightly better, and definitely not in the way you'd think.
Yeah.
They looked at a class of materials called clathrates.
Clathrates. The name sounds familiar. Aren't those the things with, like, cage structures trapping other molecules?
That's them. They're known for these really complex crystal structures.
Yeah.
Basically, frameworks made of polyhedral cages.
Yeah.
Very intricate.
And people use them for, what? Thermoelectrics, things like that?
Yeah, thermoelectric superconductors, even battery electrodes. But as electrocatalysts for something like OER, nope. This research we looked at from Dr. Menes's team seems to be the first time.
Really? So they picked a completely new type of material for this job. Which specific one did they zoom in on?
It's called Bait96G40. Bit of a mouthful.
Bait96G40. Got it. What's its structure like?
So the sources describe these cages made of germanium, which is G, and nickel, Me. And trapped inside these cages are barium atoms, Be.
Okay, so D and E form the cage. Be is stuck inside. Sounds very ordered.
Very ordered, yeah. But they decided to test this specific clathrate for the OVR reaction.
All right, the million-dollar question. Did it work? Did it help with that OER bottleneck?
It worked astonishingly well. The paper reports that at a current density of 550 milliamps per square centimeter, which is, pretty high, relevant for industry, this clathrate actually outperformed the standard nickel catalysts.
Outperform the standard ones at that kind of rate. Okay, that's significant.
It really is, and it wasn't just a flash in the pan.
What about durability? Did it last?
That was another big surprise. They ran it continuously for 10 days, and the activity barely dropped. Remarkable stability.
Wow. 10 days straight with high performance. So a material never used for this performs better and lasts longer. How? What's the secret? Especially if those normal nickel ones struggle with surface area.
Okay, this is where it gets really cool. And it's the core finding in the research. It's not just about the bar 896G40 material as it starts. It's about what happens to it when it's actually doing the job.
What do you mean what happens to it?
It transforms.
Yeah.
Like fundamentally changes its structure during electrolysis. They used some pretty advanced techniques, X-ray absorption spectroscopy while it was running.
In situ, yeah. Watching it live.
Exactly. In situ XAS plus electron microscopy afterwards. And they saw that when you put these particles in the alkaline electrolyte and apply the voltage, the germanium and the barium atoms, remember, they make up the cage walls and the trapped atoms inside. They actually dissolve. They wash out of the structure.
Hold on. The germanium and barium just leave. But isn't that most of the material?
Get this. The paper says germanium and barium account for almost 90% of the starting clathrate material, and they are completely removed.
90% washes away. What is left behind then? Just the nickel.
Just the nickel. But it's not just loose nickel atoms. What's left is this incredibly porous, like sponge-like network. Think nanothin sheets of nickel compounds, all interconnected with tons of holes.
So the ordered crystal cage completely falls apart.
Right.
And morphs into this messy nickel sponge.
Precisely. And that structure, that nickel sponge, has an absolutely enormous surface area.
Ah, there it is, the surface area problem.
Exactly. The transformation creates this massive surface area. It maximizes the number of active nickel sites that can actually touch the electrolyte and do the catalysis.
So the material basically rebuilds itself on the fly into the perfect shape for the reaction.
That's what the research suggests. Dr. Menezes points out that this means more and more active nickel centers get exposed over time as the transformation happens. It's not static. It dynamically becomes a better catalyst while it's working.
That is wild. It self-optimizes by dissolving away most of itself.
Pretty wild, yeah. And figuring this out wasn't simple.
I bet. You mentioned the techniques, the in situ XAS at places like Besicon, the electron microscope.
Right. TEM analysis after 24 hours showed that spongy net worked clearly, and elemental analysis confirmed the Shiamida were gone. It takes that kind of sophisticated work to catch a catalyst changing in real time.
And were the researchers expecting this? Or was it a surprise for them, too?
Oh, they definitely noted they were surprised by just how well the samples worked initially before they fully understood this whole transformation mechanism. It wasn't obvious from just looking at the starting clathrate structure.
So thinking bigger picture now, based on these findings, what does this mean for finding other catalysts?
Well, the major implication, and Dr. Menezes touches on this, is that this might not be a one-off. It suggests that maybe other clathrates, perhaps with different transition metals instead of nickel, could do something similar. It potentially opens up this whole new class of materials to explore for electrocatalysis. Materials that aren't necessarily amazing catalysts to begin with, but can become amazing catalysts under working conditions.
So it changes how you'd even search for catalysts. You're not just looking for the perfect static structure anymore.
Exactly. You might look for structures that are maybe designed to transform beneficially. It's a different way of thinking.
That specific paper, the one detailing this discovery, it was called
Benija clathrate transformation maximizes active site utilization of nickel for enhanced oxygen evolution performance. Published in Najuante, Zillian Chen, Prashant Menezes, and the team.
Right. A really clear example of this transformation idea in action.
Definitely provides strong evidence that this dynamic approach can yield, really top-tier results.
Okay, so wrapping up this deep dive, the key takeaway from the sources seems to be that for green hydrogen's OER problem, the answer might lie in materials that don't just sit there, but undergo these, well, radical transformations.
That's the heart of it. The clathrate becomes highly efficient and durable because it changes, creating that vital high surface area nickel network right where it's needed.
It really makes you rethink materials design, doesn't it? The catalyst isn't finished until the reaction starts. It perfects itself in the process.
Yeah, and it underlines why studying these things in operando while they're actually working is so crucial.
Yeah.
That's where the real action, the real secrets often are.
So maybe a final thought for you listening. This discovery hinges on a material dramatically changing its structure to become powerful when needed. What other materials might be out there, seemingly unremarkable, just waiting for the right conditions to transform and unlock some hidden potential we haven't even imagined?